Hi everyone, this is Professor M. Does Science, and today I want to discuss how to write general operators in terms of quantum field operators. And this is another one of our videos on rigorous quantum mechanics. Quantum field operators are the building blocks for quantum field theory. As such, we want to express all relevant quantities in terms of these field operators. And in this video, we discuss how to write general operators in terms of quantum field operators. Let's go. Let's start with a quick refresher on quantum field operators, which, as you know, are essentially the creation and annihilation operators in the position basis. The main ingredients are a discrete basis U, and we also need the continuous position basis labeled by R. We write the creation operator in the position basis as psi dagger of R in terms of the corresponding creation operators in the U basis by using the standard formula for a change of basis in second quantization. These expansion coefficients are the wave functions associated with the U basis states and take the usual form in terms of the brackets between the two sets of basis states. Moving on to annihilation operators, we write the annihilation operator in the position basis as psi of R in terms of the corresponding annihilation operators in the U basis like this. Again, the wave functions in the U basis can be written in terms of the corresponding brackets. This creation field operator here creates a particle at position R, and this annihilation field operator here removes a particle at position R. The field operators obey the usual commutation and anti-commutation relations for bosonic and fermionic operators, and we use a compact notation in which we write the commutator or anti-commutator of two operators A and B like this, where eta can take two values. It is equal to +1 for bosons, and the expression then reduces to a commutator, and it is equal to -1 for fermions, and the expression reduces to an anticommutator. In this notation, two bosonic creation field operators commute, and two fermionic creation field operators anticommute. We get a similar relationship for annihilation field operators, and for the combination of one annihilation and one creation field operator, we get the Dirac delta function. And that's it for our quick refresher on quantum field operators. For a more detailed discussion, do check out the videos where we introduce them and discuss their commutation and anti-commutation relations, and you can find all those videos linked in the description. What we'll do in this video is to explore how to write general operators in terms of the creation and annihilation field operators. Let's start with one-body operators. Now, what do we mean by a one-body operator? These are operators that act on systems of many identical particles, but act on one particle at a time. For the full details on these one-body operators, you can check out the corresponding video linked in the description. Here we'll just have a brief summary of their properties. First, consider the single particle state space VQ, and an operator FQ that acts on the single particle state space. Let's now build an n-particle system described by the state space V, which is explicitly given by this long tensor product over the individual single particle state spaces. The single particle operator FQ that acted on a single particle state space can now be promoted to an n-particle operator that acts on the n-particle state space like this, where all entries correspond to the identity operator apart from the entry acting on the subspace VQ. This operator acts on the full state space, but its action only affects one particle, as it only acts non-trivially on the subspace VQ of the full state space. For convenience, we typically don't write all the identity operators and simplify the expression to FQ. But do make sure you understand that this operator here, which acts on a single particle state space, is different from this operator here, which acts on an n-particle state space. From the context, it should be clear which one we talk about, but if it isn't, then we'll aim to include the longer expression for the operator acting on the n-particle state space, including the corresponding identity operators. From these operators acting on individual particles, we can build a symmetric one-body operator, capital F, acting on the full state space V, and we define it as the sum over all particles of the individual operators acting on each of the individual particles. This one-body operator F now acts on all particles, but it does so by acting on each particle separately. One-body operators of this form are very common for the description of quantum systems. An important example is the kinetic energy operator. In general, we want to write down these one-body operators in second quantization, and in this video we'll explore how to do this in terms of field operators. Let's make some room, and let's write down a general one-body operator. From our video on one-body operators, we know that in the discrete basis U, we can write down a one-body operator in second quantized form as equal to the sum over ij of the matrix element ij of the single particle operators times the creation operator for the basis state ui and the annihilation operator for the basis state uj. We often write the matrix element in a more compact form like this, and we can then rewrite our expression in this simpler form. Given this, how do we write the one-body operator F in terms of field operators? Well, field operators are nothing more than a continuous version of the usual creation and annihilation operators, so we can extend this same formula to the continuous case. We work in the continuous position representation, and we get that the one-body operator F is equal to an integral over R1 and an integral over R2 of the matrix element R1, R2 of the single particle operator times the creation field operator at R1 and the annihilation field operator at R2. And that's it. This is our one-body operator in terms of creation and annihilation quantum field operators. Let's make some room again. Although the expression we've just obtained is perfectly valid, it's a good exercise to rederive the same result by explicitly converting the expression of the one-body operator in the U basis into the position basis. So that's what we'll do next. To do so, we start by writing F in its usual form in the U basis. We then remember from the video on field operators that we can write the creation operator in the U basis in terms of the creation field operators like this, and we can also write the annihilation operator in the U basis in terms of annihilation field operators like this. Inserting this expression into this term and this expression into this term, we can rewrite our one-body operator F in this long form, where we first have the sum over the matrix elements, then we replace the creation operator in the U basis by its expansion in terms of creation field operators, and then we replace the annihilation operator in the U basis by its expansion in terms of annihilation field operators. The next step is just to rearrange the terms in our expression in this more convenient form. And feel free to pause here for a moment to double check this step, but really all we've done is to rearrange some terms. Moving on, this here is the resolution of the identity in the U basis, and this here is also the resolution of the identity in the U basis. Using these results, we end up with an integral over R1, an integral over R2, the matrix elements of the single particle operator F in the position basis, and finally the creation field operator at R1 and the annihilation field operator at R2. And that's it! We've now obtained the same result we got earlier by explicitly moving from the U basis to the position basis. The other important type of operators in quantum mechanics are two-body operators. And an example is the all-important Coulomb interaction between two charged particles. We can directly write a two-body operator G as equal to this symmetrized sum over two particle operators little g. And these operators G, Q, Q prime act on the subspace VQ tensor product VQ prime. In second quantized form, in the U basis, this two-body operator G is written as 1/2 sum over the four indices I, J, K, L of the matrix elements of the little g two-particle operators, and then the creation operators associated with the Ui and Uj basis states, and also the annihilation operators associated with the UL and UK basis states. You can find full details about two-body operators in the video linked in the description, but just as a quick reminder, I'll note a few things about the notation. First, it's important to remember that the order is K here and L here in the matrix element, but is the opposite, L here and K here, in the associated annihilation operators. Second, without loss of generality, we can write the two-particle little g operator with the subindices 1 here and 2 here. And similarly, the basis states from state space V1 here, and from state space V2 here and here. This is because each of these little g operators acts in the same manner on any pair of particles from our n-particle system. And again, these results are discussed in much more detail in our video on two-body operators in second quantization, which is linked in the description. So if you need a refresher, do check that video out. Now, to write these two-body operators in terms of field operators, all we need to do is again to remember that field operators simply correspond to the creation and annihilation operators in the position representation, which is a continuous representation. Using this insight, we can directly write down the two-body operator G as equal to 1/2 times 4 integrals over R1, over R2, over R3, and over R4 of the matrix elements of the two-particle little g operator in the position basis, and finally the associated creation operators at R1 and R2, and the associated annihilation operators at R4 and R3. And again, note that the order in the matrix element is R3, R4, whereas the order in the annihilation operators is R4, R3. Let's summarize our results so far. We can write a one-body operator F in terms of field operators using this very long expression. And we can write a two-body operator G in terms of field operators using this even longer expression. How can we conceptually understand these expressions? Starting with the one-body operator, the integrand involves the annihilation of a particle at position R2 and the immediate creation of a particle at position R1. This process is then associated with this matrix element, which is just a number that tells us the relative amplitude associated with this transition. So one very natural way to interpret this expression is in terms of scatterings of particles from a position R2 to another position R1, with each transition being associated with a certain amplitude given by the corresponding matrix element. The full one-body operator includes all scatterings for single particles from all possible starting positions to all possible final positions, and each is associated with its own amplitude. All one-body operators have this form, and they only differ in the matrix elements, which determine the relative importance of each scattering event. Moving on to two-body operators, we can understand them in a similar way. But now the integrand describes the scattering of two particles at initial positions R3 and R4 to the new positions R1 and R2. Again, the amplitude of this process is associated with the corresponding matrix element. From this point of view, one-body operators involve the scattering of individual particles, while two-body operators involve the scattering of pairs of particles. This is exactly why we call them one-body and two-body operators. Let's make some room. So far, we've been ignoring the spin degree of freedom of our particles. What we need to do now is to remember from our video on quantum field operators how we can extend them in the case of spinful particles. And in a similar way, we can extend our expressions for one-body and two-body operators. For one-body operators, we get this long expression for identical particles of spin s. The key is that now the field operators have two labels, the usual continuous position label here, and the new discrete spin label here and here. In a similar manner, the matrix elements are now taken with respect to basis states that include both position and spin indices here, and the integrals over the continuous position degrees of freedom need to be augmented with the summations over discrete spin degrees of freedom. For two-body operators, we make a similar extension and end up with this even longer expression, where I'm omitting the summation limits and integration limits. We then have the usual matrix elements. And I cannot really fit the whole thing into a single line, so I'm writing the creation and annihilation field operators in this second line. To finish the video, let's look at a simple example. Consider the single particle operator written as the outer product of the basis state R with itself. Now, for a single particle, what does this operator do? To answer this question, let's calculate the expectation value of our operator in an arbitrary state phi. Inserting the definition of f, we end up with this expression. This bracket here is just our state in the position representation, which is simply the wave function phi of r. And this bracket here is the corresponding adjoint, so we obtain the complex conjugate of the wave function. Bringing everything together, we end up with the absolute value squared of the wave function associated with our state phi. Now, in the position representation, the absolute value squared of the wave function gives the probability distribution of finding the quantum particle at a given location in space. This means that our operator is associated with the local single particle density at position r, and we can write it in the more usual form, n of r. Let's now build the associated local particle density one-body operator for a system of n identical particles using the usual symmetric sum. Now, what does this operator look like in second quantized form? In the discrete basis u, the operator takes its usual form as a sum over ij of the matrix elements times the associated creation and annihilation operators. This bracket is equal to the wave function associated with the basis state uj, and this bracket is the corresponding complex conjugate wave function of the basis state ui. Putting everything together, the local particle density operator takes this form in second quantized form in the u basis. Finally, moving on to the position basis, to write it in terms of field operators, we can write the one-body operator as this integral over R1 and this integral over R2 of the matrix elements in the position representation times the associated creation and annihilation field operators. This bracket here is equal to this Dirac delta function, and this bracket here is equal to this other Dirac delta function. We end up with this long expression. The integrals are now trivial thanks to the two Dirac delta functions, and we end up with the creation operator at R times the annihilation operator at R. So, the local particle density operator in terms of field operators takes a particularly simple form. The operator annihilates the particle at R and then creates it back at the same point. We should have expected that this operator, which only involves position eigenstates, should take a particularly simple form in its own position representation. In any other representation, such as that of the U basis up here, the operator doesn't look as simple. One-body operators and two-body operators are the most common type of operator that we work with in quantum mechanics. And now we know how to write them down in terms of quantum field operators. As an example, you can check out our video in which we write the Hamiltonian of a system of identical quantum particles in terms of these quantum field operators. And as always, I hope you liked the video and please subscribe.